Welcome to this video, where we will explore one of the most fascinating and mysterious concepts in quantum physics, wave-particle duality. This principle reveals that quantum objects, such as electrons and photons, do not behave exclusively like particles or waves, but can display properties of both, depending on how we observe them. Understanding wave-particle duality is key to unlocking the strange behavior of the quantum world, and today we'll break it down in simple terms. In classical physics, waves and particles are distinct entities. Particles, like tiny billiard balls, have a definite position and move along a specific path. Waves, like water waves or sound waves, spread out, interfere with one another, and can create patterns of peaks and troughs. In our everyday experience, these categories seem separate and obvious. A rock does not behave like a ripple on a pond, and light does not behave like a solid object. Quantum physics, however, blurs this distinction. Experiments show that particles like electrons, protons, and photons can behave both as discrete particles and as waves, depending on how they are observed. This duality is at the heart of quantum mechanics and challenges our classical intuition. The most famous demonstration of wave-particle duality is the double-slit experiment. Imagine shining light or sending electrons toward a barrier with two narrow slits. If we try to observe which slit a particle passes through, it behaves like a particle, going through one slit and producing a predictable pattern on a screen behind the barrier. But if we do not observe the path, the particle behaves like a wave, passing through both slits simultaneously and creating an interference pattern, a series of alternating bright and dark bands. The very act of observation determines whether the particle behaves like a wave or like a particle. This experiment shows that quantum objects do not have a fixed behavior independent of measurement. Their nature is not simply wave or particle, it is both, and which aspect we see depends on how we interact with the system. The wave aspect describes the probabilities of where a particle might be found, while the particle aspect becomes apparent when a specific outcome is measured. Wave-particle duality is not limited to photons or electrons. Even large molecules, such as buckyballs, have been shown to exhibit interference patterns when carefully controlled in experiments. This demonstrates that wave-like behavior is a fundamental property of all matter at small scales, not just light. The larger the object, the harder it is to observe these effects due to interactions with the environment, but the principle itself remains true. This duality has profound implications for technology. Understanding the wave nature of particles allows for the development of devices like electron microscopes, which use the wave properties of electrons to produce images far sharper than possible with light. It also underpins quantum computing, where particles in superposition behave like waves, enabling multiple calculations to occur simultaneously. Wave-particle duality also illustrates the probabilistic nature of quantum mechanics. When we describe a particle as a wave, we are actually describing a wave function, a mathematical representation of the probabilities of finding the particle in different places. The interference pattern in the double-slit experiment emerges from the combination of all these probabilities. When we measure the particle, the wave function collapses, and we see a specific outcome. Philosophically, wave-particle duality challenges our classical understanding of reality. In the macroscopic world, objects have definite properties independent of observation. In the quantum realm, the properties of particles are not fixed until they are measured. This leads to fundamental questions about the nature of reality, observation, and the limits of human knowledge. In summary, wave-particle duality is the principle that quantum objects can exhibit both wave-like and particle-like behavior. Their apparent nature depends on how we observe them, and this duality is a fundamental feature of the quantum world. It explains the behavior of light and matter, underlies key quantum technologies, and highlights the strange and counterintuitive rules that govern the microscopic universe. By understanding wave-particle duality, we gain insight into a world where particles can act like waves, probabilities guide outcomes, and the act of observation plays a central role in shaping reality. This principle is one of the cornerstones of quantum mechanics, revealing that the universe at its smallest scales operates in ways that defy classical intuition. Thank you for joining this exploration of wave-particle duality. As we continue to study quantum mechanics, this phenomenon reminds us that reality is far more complex, fascinating, and mysterious than our everyday experience suggests. And that the universe at its smallest scales is full of surprises.